Hey guys, so today we're going to continue our march through our lectures regarding functions for the Transitions to Advanced Mathematics course. And today we're going to cover bijections and inverses. So in the previous lecture we covered injections and surjections, and so we know that an injective function and a surjective function are special kinds of function because they have some special properties. Well, if we combine those two properties, we get a super special awesome function. Okay, and we call those super special awesome functions bijections. Okay, so here's just the definition of that. A function from a set A to B is a one-to-one correspondence or a bijection, and I'm going to use the word bijection throughout, if and only if f is injective and surjective. Okay, and I showed several examples of how to compute whether or not a function is an injection or a surjection in the previous lecture, and so I'm just going to leave the definition at that. In order to show a function is a bijection, you have to show that it's both an injection and a surjection. And if you don't remember what those terms mean, please review the previous lecture on injections and surjections. Okay, there's a analogous theorem to injections and surjections for bijections. So if fa to b is bijective and g from b to c is bijective, then the composition of the two functions from a to c is bijective. And this basically follows from the previous lecture where we showed that the composition of surjective functions is surjective and the composition of injective functions is injective. And so therefore it follows that the composition of two bijective functions is also going to be bijective. The next theorem we're going to discuss sort of gives perspective on when we can say that the inverse of a function is a function itself. So remember when we introduced the idea of an inverse of a function, we said it was the inverse relation for a function because the inverse of a function was not always a function. So in this next theorem, we're going to show what conditions guarantee that the inverse of a function is a function. So let's look at this theorem. So theorem. So let f be a function from a to b. Okay. Part A of this theorem says f inverse is a function from the range of f to a if and only if f is injective. And part B of this theorem says if f inverse is a function then f inverse is injective. Okay, so this tells us that basically in order to guarantee that the inverse of a function needs to be a function, we just need the original function to be injective or one-to-one. Okay, so yeah, we can go ahead and prove this. So proof for part A. So assume f inverse is a function from the range of f to a. Okay, so remember part A of this theorem is a biconditional statement, and so we have to prove both directions here. So first we're going to assume that f inverse is a function from the range of f to a. Need to show f is injective. And how do we show that? Assume f of x equals f of y, both equal z. Then xz and yz are both elements of f, right? Therefore, if you flip those ordered pairs, you get that zx and zy are both elements of the inverse function. But since f inverse is a function, that's the key word, we have that x equals y, which shows that f is injective. Because remember, because f inverse is a function, the same element in its domain cannot be mapped to two different elements. And so x and y must be equal. Okay? Now assume f is injective. Need to show f inverse is a function from range of f to a. So let xy and xz both be elements of f inverse, right? Then yx and zx are both elements of f. Since f is injective, we have that y equals x. Okay? So that finishes that proof. Okay, part B. So part B says that if f inverse is a function, then f inverse is 1 to 1. So need to show is injective if f inverse is a function. So let xz and yz both be elements of f inverse. And then zx and zy are both elements of f, and from the previous part A of this theorem, we know that if f inverse is a function, then f must be 1 to 1. So f is injective. So actually, we might not even need that because f is a function. Immediately we have that x equals y. So that finishes that proof. So sorry for the little hiccup there. So basically what this tells you is that for a function to have an inverse that is a function itself, you just make sure the function is injective. Okay, so here's a nice little corollary. the inverse of a bijection is a bijection. Okay, so that's a nice little corollary, and you can think about how to prove that, but it's pretty straightforward. The next theorem I'm going to talk about gives us a nice sort of way to think about all these ideas we've been discussing for the past couple of lectures. It also gives you an easy way to compute the inverse of a given function, or to understand when a function is indeed one-to-one and onto without explicitly doing such a calculation. So theorem: let f be a function from a to b, and g be a function from b to a. Part 1 says g equals the inverse of f if and only if g composed with f equals the identity mapping, okay, on the set A, and f composed with g gives you the identity mapping on B. Okay, so notice the word and here. Secondly, if f is a bijection, then g equals inverse of f if and only if the composition of g with f is the identity on A, or, so notice the word or here, the composition of f with g equals the identity on B. So you only have to check one of the compositions to see if one function is the identity, if one function is the inverse of the other. So what does this theorem say? This theorem says that if I give you a function and then you apply, if I give you an element in a set and you apply a function to that element, and then you apply the inverse of that function to the image, then what's going to come out is the original element itself. So this is something that you all have seen in some of your calculus classes. So, for example, for all x greater than 0, e to the natural log of x equals x. And for all x in real numbers, right, the natural log of e to the x equals x, right? So in the first example here, I've given you an element in the real numbers, the positive real numbers, and then you applied the log to it, and then you exponentiate it, and then you got the number back. In the second case, I gave you any real number. I first exponentiated it, then I took the logarithm, and then I got the element back. Okay, so that's what this theorem up here says. We can look at a more complicated example. So, example. Let h of x be equal to x squared plus 2 if x is less than 0, and 2 minus x squared if x is positive. This map is a bijection on the real numbers. Show the inverse of that function equals k, where k of x equals the negative square root of x minus 2 if x is bigger than or equal to 2, and the square root of 2 minus x if x is less than 2. Okay, so one key point here is that h is a bijection, and so we only need to check one way or the other. Okay, so we're going to do it in the following way. So there are two cases. One, x is less than or equal to 0, and 2, x is positive. That's just given from the piecewise definition of h up there. If x is less than or equal to 0, h of x equals x squared plus 2. K of h of x equals negative sorry, let's not go there yet. Yeah, anyway, yeah. K of h of x is equal to the negative square root of x squared plus 2 minus 2, which equals negative square root of x squared, and now x is less than or equal to 0, and so this is going to be equal to minus the absolute value of x, which is just going to be equal to x. Now, why did I choose this structure for k as opposed to the other, because k is also piecewise defined? Well, what I'm plugging into k is x squared plus 2. So use this branch of k because x squared plus 2 is bigger than or equal to 2. Okay. Now, if x is bigger than 0, if x is bigger than 0, then h of x equals 2 minus x squared, which is less than 2. And so k of h of x is going to be equal to the square root of 2 minus x squared, which is square root of x squared, which is x. Okay? So inverse of h equals k. Done. Another important thing that these inverse calculations can teach you is that if two functions are inverses of each other, then you can also say something about them being one-to-one and onto. But we're going to finish up this section by talking about a very specific type of bijection, which is studied quite intensely in abstract algebra, and they're kind of fun to play with. So let A be a non-empty set. A permutation of A is a bijection from A to A. So you define a function on a given set, and if that function from the set to the set itself is a bijection, you've actually constructed a permutation. So why is it called a permutation? It's because if you define a function from a set to itself, basically the image of a given function produces another element in that set, and so in effect you've effectively just moved around the elements of that set. Okay? So example. Let A equal just the simple set 1, 2, 3. So the identity function is a permutation of A. The following function t, given by 1, 2, 2, 1, 3, 3, that's a permutation. And the next one, 1, 2, 2, 3, 3, 1, that's a permutation of the set A as well. And so one thing that people like to do, especially when they're thinking about permutations of like small finite sets like this, is to write in this sort of image format what the permutations are doing to the set A. And so let me say what this image format is. I'm going to write image format for each of these permutations on the right hand side here. So for the identity element, for the identity permutation, so you open the bracket, and then you're going to have three elements or three items listed in these brackets, one for each element of A, 1, 2, 3. And then you ask, what is 1 mapped to under the identity? Well, it's mapped to 1. What is 2 mapped to? 2. What is 3 mapped to? 3. And so if you write this format here, you've actually captured all the information of the identity permuting the set A. The function, the permutation t here, what does 1 get mapped to? 1 gets mapped to 2. What does 2 get mapped to? 1. You don't need these commas. 2 gets mapped to 1, and 3 gets mapped to 3. And what about S? S1 gets mapped to 2, 2 gets mapped to 3, and 3 gets mapped to 1. And so, yeah, that's an interesting way to write things. So another example, just to maybe get you used to this notation, is the following. Let H be equal to the following. 4, 2, 6, 5, 3, 1. This permutes B equals just the first 6 natural numbers. And in particular, H equals the function 1, 4, 2, 2, 3, 6, 4, 5, 5, 3, and 6, 1. Okay, so notice how much easier it is to write this bracket notation up here. So another advantage of these sort of bracket notation is to compute compositions and inverses. So let A equal 1, 2, 3, 4. Let T equal the permutation 2, 4, 3, 1, and let S be the permutation 2, 3, 1, 4. Now let's compute composition of T and S, which is going to be 2, 4, 3, 1 composed with 2, 3, 1, 4. And we want to write a bracket notation for it. And so we want to ask, under this composition, what is 1 mapped to? Well, first you start with the one on the right. So start here. Under this right hand, under S, what is 1 mapped to? 1 is mapped to 2. That's what this little information here says. So 1 is mapped to 2. And then under T, what is 2 mapped to? 2 is mapped to 4. And so ultimately you get 1 is mapped to 4. 2 is mapped to 3, and then 3 is mapped to 3. So you get 3. 3 is mapped to 1 under S, but then 1 is mapped to 2 under S. And then just for sanity check, 4 is mapped to 4 under S, but then 4 is mapped to 1 under T. So you get 4, 3, 2, 1. You can also quickly find inverses. So what if we want to find the inverse under bracket notation? Well, you just look at what 2 does. You look at what T does to each element. T, so I'm just going to write T here, is 2, you don't need the parentheses, sorry. It's 2, 4, 3, 1. So what does T do to 1? Well, T map takes 1 to 2. And so the inverse is going to take 2 to 1. T takes 2 to 4. So the inverse is going to take 4 to 2. T takes 3 to 3, and so this will also take 3 to 3. And T takes 4 to 1, so this is going to take 1 to 4. And to check this, you can always compute the composition. So let's finish off by doing that. 4, 1, oops, may put more space. 4, 1, 3, 2, composed with 2, 4, 3, 1. Just make sure I got that. Okay. So we want to compute this. So 1 gets mapped to 4, then 4 gets mapped to 1. 1 gets mapped to 2, and then 2 gets mapped to 1. 2 gets mapped to 4, and 4 gets mapped to 2. 3 gets mapped to 3, and then 3 gets mapped to 3. And then 4 gets mapped to 1, and then 1 gets mapped to 4. And that's the identity. And so that proves that they're inverses, and so we haven't screwed up anywhere. Okay, I hope you enjoyed that lecture. I hope you really enjoy the permutation part. It's a bit of abstract algebra, which I think everyone should get a sort of grasp on. And alright, I'll see you in the next lecture. Hope you enjoyed it. Bye.